Do you conduct a business in the Plenty Valley or surrounding area? If so, consider Plenty Valley FM 88.6 for your business promotion. Our rates are reasonable and results positive. Call 9404 2111 during business hours for more information.
Welcome to the podcast series Spaced Out Down Under, hosted by author-journalist Eden White and journalist-broadcaster Denise Kuchma. Spaced Out Down Under aims to give a voice to astrophysicists, cosmologists and others in the physics and astronomy field to share their research and discoveries about what's happening in the cosmos. Episode 1 explores the new field of astronomy. Dr. Lasky is an associate professor, head of Monash Astrophysics at the Monash University in Victoria. His interests include a variety of topics under the broad heading of gravitational astrophysics. He has a particular attraction for gravitational wave astrophysics. Dr. Lasky is a highly regarded member of the Parkes Pulsar Timing Array. He's also heavily involved with LIGO, Laser Interferometer Gravitational Wave Observatory scientific collaboration that has witnessed one of the biggest astronomical discoveries of the 21st century. Welcome to Spaced Out Down Under, Dr. Lasky.
Thank you. Thanks for having me.
What was the discovery?
Back in 2015, we made the first discovery of gravitational waves, and gravitational waves that came from the collision of two black holes more than 1 billion light years away. These two black holes were a lot more than the mass of our sun. So one of them was around about 35 times the mass of our sun. The other was around about 29 times the mass of our sun. And these two black holes were caught in a death spiral, circling around one another. And then they eventually collided with each other. And we detected this as tiny, tiny ripples of gravity using this LIGO gravitational wave observatory, which is the most precise measurement ever made on Earth. And allowed us to measure these gravitational waves, not just measure these little ripples of the fabric of space-time, but also to actually infer the astrophysics. And we could work out the masses of these two black holes. We could work out how they were spinning. We could work out what they look like and, if they agree with Einstein's theory of general relativity and all of these kinds of things.
In all your career to date, did you ever think that your secondary college physics would ever lead you to the types of discoveries that you've been experiencing?
I guess I just fumbled through my career, never really thinking about that, to be honest. I was always very excited about gravitational waves and about the prospects of making detections. For a long time, the first discovery was made in 2015. I was a member of the LIGO collaboration, I think from around about 2011, but working in the field of relativistic astrophysics for a number of years before that as well. It was always on the horizon. That we were going to make an observation like this. And, in fact, we've made 100 more of those observations ever since, and we're doing it regularly now. But it was always something that you look forward to and you didn't really know what to expect. And I think it was actually an even bigger deal once it was there in front of us, once we really saw that data, saw what these things looked like, really started to understand what we can learn about the universe, that we'd been speculating on these things, and you sort of write down ideas and you write papers that say, once we discover gravitational waves, we'll be able to say X, Y, and Z. But actually, it's not until the rubber hits the road and you have this data in front of you and you have this awe-inspiring sense of where this data has come from, and this incredibly precise measurement from one of the most explosive things that has happened in the universe. But that explosion gave off no light. It just gave off these ripples of gravity. And to be able to hold that in your hand and say, this is the data, and stare at it and play with it and turn it around every which way and say, what can we learn from this? I think that was, for me, part of the most exciting part. Did I expect that? I don't know. I really don't know.
What lured you to Monash University in particular?
Yeah, Monash has always been home for me. I grew up not that far away from Monash, so went to school sort of 15 kilometres down the road. So I came here to do my undergrad, wanted to study science. I was just passionate about physics, mathematics, already had an excitement for black holes when I was very young. Monash was the obvious thing. Finished my undergrad and I don't know, again, this is me fumbling through a career. I just looked at it and thought, well, I worked with a great supervisor through my honours year at Monash. So I thought, there's no point going anywhere. I'm happy. I'm comfortable. I was living with a couple of mates and, living the good life. My girlfriend at the time, who's now my wife of however many years, was studying here as well. So everything was happy. Everything was hunky-dory. So I stayed, did my PhD, but then sort of travelled the world, did postdocs overseas and did all of that. And really, when I came back here, that was a really exciting moment to, I know how good the university here is. I know how good the School of Physics and Astronomy is. I'm now, the head of the Monash Astrophysics group, which has been, a whirlwind ride. It's been amazing. It's just so wonderful. It's such a strong group and such amazing colleagues to be working with. We get amazing students coming through here the whole way from undergraduate through to postgraduate. So it's just a really exciting place to be. It's fantastic.
Need we ask, what was the topic of your PhD?
Yeah, it's not a good question. I have some regrets about this, actually. It's interesting. I'm not sure if I'm supposed to admit that. My PhD topic, I'm trying to remember the exact name. It was something along the lines of a unified model for gravitational collapse in general relativity.
Wow.
Yeah. And the reason I say I have some regrets is that, I graduated from a PhD in 2008 and we were working on problems in my PhD that were very relevant in the 1960s, and no one really cared about it after the 1960s. And so it was this sort of esoteric kind of hybrid between really sort of some hardcore mathematics but only loosely related to the physics and astrophysics. And I realized towards the end of my PhD that actually I'm more interested in the physics and the astrophysics. How does this apply to something in the universe? How can I get my hands on something in the universe that, allows us to learn actually cutting edge things? And so that's when I really started pivoting towards trying to understand how neutron stars work in our universe, trying to understand how black holes work in our universe, trying to understand gravitational waves and things along those lines, because I really wanted to get my hands dirty both at the interface, I guess, with the data and cutting edge data from the amazing instruments that people are building all around the world, both in terms of gravitational waves, but also classical electromagnetic telescopes, X-ray observatories, radio observations, which are amazing throughout the world, including in Australia, optical things like Hubble and now JWST and in the UV and things like that. So yeah, this is the way of trying to get away from my PhD from your actual question here. That I sort of have moved a long way away from that. But I learnt a lot, and it was a fantastic experience. So.
Eden.
Paul, thanks for coming this morning. When I think about gravitational waves, I think many of the listeners would think of maybe of a tsunami or something when you've got an event under the water and creates a response to that event. And I'm thinking gravitational waves, you've got an enormous explosion in space. When you dig down a bit, what is a gravitational wave? I know Einstein talked about it himself in 1915. What's your take on when you drill down? We're not probably drilling down to the quantum side of it, but
no.
How do you describe?
Yeah, look, you don't need to drill down to the quantum side of it at all. It's a very classical thing. So absolutely in 1915, Einstein writes down his theory of general relativity and the equations that we now use to understand gravity throughout the universe. 1916, he writes down that there's actually this prediction that these things called gravitational waves should exist. He himself says around that time, well, they should exist, but we'll never measure them. They're so tiny that there's just no chance of measuring them. You actually fast forward a number of years or a number of decades through the sort of 30s, 40s, 50s, there was this huge debate whether they do even exist or not. And it wasn't until I believe it was Feynman in the sort of late 50s who actually came up with this really beautiful thought experiment, which was backed up with a lot of mathematics, but showed that gravitational waves can dissipate energy. And the fact that they can dissipate energy really means that they're physically real. What are they? They really are ripples of gravity. But that's a weird phrase, and it sort of doesn't necessarily help to understand it. What do they do physically, I think, is the more interesting question. You and I are sitting here about a metre apart at the moment. If a gravitational wave were to pass between us, it changes the physical distance between you and I. Now, it does that on an absolutely tiny scale, and that's the reason that it took 99 years for the first discovery of gravitational waves, for them to be first directly seen with an experiment designed to detect them. But it really is that physical distance that changes. So the way we measure these then is with what's called a laser interferometer. The laser interferometer has two arms that run off perpendicular to one another, and they send this very high-powered laser. It's actually a coherent laser, so you send one laser into this. That laser gets split into two so that it's the same laser light that's going down each of the perpendicular arms. Those arms are 4 kilometres long, and so we're trying to measure a change in distance over that 4 kilometres. And it turns out that the way a gravitational wave works is that it will simultaneously make one of the arms longer and the other arm will get shorter at that time. But it will get shorter by the amount, approximately 1/1000th the size of a proton. It's just a ridiculously small amount. This is why we say this is the most precise measurement that's ever been made, because it truly is. You're measuring something that is significantly smaller than a single atom, significantly smaller than the nucleus of a single atom. And you're measuring that change over a 4 kilometre length. It's a ridiculous experiment when you phrase it like that. It shouldn't be possible. It is. Brilliant people, thought up how to do this, designed the whole thing, understand all of the different noise sources and all of these types of things, and now we use it regularly to do astrophysics. It's truly remarkable.
So, Paul, are we changing the curvature of space-time in a way?
Well, we're not manipulating it at all.
The waves themselves.
The waves are, in a sense, they are the curvature of space-time.
Yeah.
That's exactly right. So general relativity is this concept that gravity is not a force. Gravity really should be seen as the curvature of four-dimensional space-time. Okay, and so when you start thinking about gravity not being a force, and some people call it a pseudo-force and things along these lines, but when you start thinking about it just being the manifestation of this curved four-dimensional space-time, which is a weird thing to think about, mathematically that's all it is, and you can write that down, and I was going to say easily, but we teach it at fourth year level here. It's pretty tough mathematics, but you can write it down. It is that curvature of space-time that is changing and that is undulating, and there's a wave that travels in that curvature of space-time. And you can very easily write down that wave travels at the speed of light, and when I have two very, very massive objects like two black holes, and they're moving incredibly fast, they're moving up to 0.6, 0.7 times the speed of light, so incredibly fast for these really big macroscopic objects, that generates a lot of gravitational waves, and they give off a lot of power in gravitational waves. There's a huge amount of power that comes off these things, all in gravitational waves, and yet the ripples that they create are so tiny. And that's this sort of really paradoxical thing about gravitational waves.
I can see, Paul, the fascination in the way you talk about this, and it's really quite pleasing. But the question I have, and a lot of people say, is how far can these go? Like light will go on and on and on. Do gravitational waves, the energy within them, allow them to go forever, infinitely?
Yes, I mean, infinite's always a funny word. Yeah. It's a very mathematical word. Absolutely. So, in fact, in some sense, they're quote unquote better than light for various reasons, and I can sort of explain this. So, if I have a source of light, then that falls off like the distance, 1 on the distance squared. So what that means is that if I'm 2 times further away, then I've got 4 times less light essentially reaching me. That's true in gravitational waves in the sense of the energy of the gravitational wave falls off the same way. So I get, if I'm twice as far away, I get a quarter the amount of energy in gravitational waves. But I don't measure the energy of gravitational waves. What I measure is the amplitude. And the amplitude only falls off like the distance. So if I'm 2 times further away, I only get half as much signal rather than a quarter of much signal. So that's a really fantastic way to say that actually now that I can start seeing gravitational waves, and we've been doing it since 2015, we can actually start seeing them by making our instruments more sensitive. We can start seeing them really out to the other edge of the universe much, much more easily than we could with electromagnetic light, with standard light, because of this different effect where we're measuring the actual amplitude that falls off linearly with the distance. So we're planning next generation of gravitational wave observatories. They're huge instruments that require a lot of research and technology development and things along those lines, and I'd be more than happy to talk about all of that. But though that next generation of instruments, if we're successful with them, they will see every single merger of a black hole in the entire universe. They can see that far that they can just see out to the complete other edge of the universe. The universe doesn't have edges, but so truly remarkable. Whereas, the technology for doing that with light has taken a long time. So you can even go a little bit further back. I mean, you can say, well, at what point should black holes start merging through the universe? And we have some sense of the answer to that. But there are probably gravitational waves that got generated actually almost immediately after the Big Bang, 10 to the minus 30 seconds after the Big Bang, through a period called cosmic inflation. You get these little quantum fluctuations of the density field that seed little gravitational waves. And there is a chance that we will be able to see those gravitational waves from the initial seeds of the universe. And that would be truly mind-blowing, truly remarkable, but we'll be able to learn so much about the universe because you cannot get light back that far. No. Light, the furthest back light can go is about 300,000 years after the Big Bang, because that's when the universe becomes opaque. And so you just physically cannot see further back than that, and you never will be able to. But with gravitational waves,
they come through.
They come through,
and you can't stop them.
Unimpeded. Yep.
With all this talk about gravitational waves and, of course, the observatory that measures these waves, I understand that LIGO is like no other observatory in appearance. So what does it look like and how does it work?
Yeah, they're truly remarkable. They have a central station, which is a sort of big building that when you walk into it, it looks like an incredibly large but sort of clean lab. You have to put on your little socks and booties and you have to wear your hairnets and things. I don't have much hair left. So truly remarkable experiment. So that's a really big building. It's got huge vacuum tubes that sort of stretch up to even higher than the roof, because we've got these mirrors that I was sort of briefly mentioning before. Actually, the mirrors that bounce this laser light in the cavity, you want to isolate them away from any kind of seismic motion, so any ground noise. And when I say ground noise, it's not seismic motion in the sense of, if there's an earthquake in the ground, that's a problem. It really is, if there's a truck driving down the road 2 kilometres away, that's a problem. We measure that. So these 4-stage pendulum systems where you've got a huge 40-kilogram mirror that hangs off the bottom of a 4-stage pendulum. Each pendulum's about 1 metre high, and so it's, really a monolithic thing. And that's to get rid of all of these different seismic noises and different noise sources that you just don't want. So that's in this sort of base station. And then there's sort of a lot of optical benches where you have lasers bouncing around all different cavities and, trying to get the laser light exactly how you want it and enough power into it and things along those lines. And then the laser light goes off into this half-silvered mirror, which causes the light, half of the light to go in one direction, the other half of the light to go in the other direction. And they really do bounce down this 4-kilometre long arm, which is a vacuum tunnel. So it's a vacuum tube that I think the radius of the vacuum tube is about 10 centimetres wide, which means you think about, I've got to get this laser going 4 kilometres not to hit the edge of that. The edge of that.
Yeah, I was wondering about that.
Luckily, this is the experimentalist's problem. And not only that, but in fact, the laser light travels that 4 kilometres, it bounces off another one of these 40-kilogram mirrors that's being suspended on a 4-stage pendulum system, and then it bounces back. And in fact, it bounces in and inside that cavity around about 1,000 times before it comes out. So not only do I need to align it, when I say I don't do this, I'm a theorist, I deal with the data, I let other people do this, they don't let me near the experiment. That light has to be so accurately pointed that it's hitting really the middle of that mirror at the other end, so that it bounces exactly up and down this tunnel, 1,000 times 4 kilometres without hitting a 10 centimetre wide thing. It's truly remarkable. So if you look from above, it just looks like 2 arms that go off 4 kilometres in either direction. But once you dig down inside the experiment, it's really the amount of engineering and fundamental sort of experimental physics that goes into this experiment is truly remarkable.
Imagine it's in a very secluded area, so people can't go anywhere near it. So your data comes through
That's right.
as authentic as it can.
That's right. So we have 2 instruments in the US, and there's another instrument in Italy, just near Pisa, The instruments in the US, one of them's in a place called Livingston in Louisiana, so down in the sort of deep south. It's a few hours out of Baton Rouge, and halfway between Baton Rouge and New Orleans. It's in the. You've got to be careful of the gators. You've got to. You sort of, it is sort of swampy marshland. It's a gorgeous area. It's really pretty.
Very good protection.
Very good protection. But there are trucks driving not so far away, which can cause issues, and you can see that the sensitivity of the instrument goes down during peak hour and things along those lines. But it's the other instrument in the US is about 1,000 kilometres away, and we do that because if you do have a noise source, it will affect one of the instruments and not the other, right? If that truck drives past and causes a big noise source, we'll see it in one instrument, but we won't see it in the other. So we go, okay, great, that's not an astrophysical signal, right? So the other one is up in Washington. In northwest of the US, about 1,000 kilometres away. That one's on a nuclear reserve. And so that's, good use of land. Yeah, and so the fact that we have these two instruments and then actually this third one just near Pisa in Italy, that's slightly less sensitive but is still a remarkable and beautiful instrument and has made many detections of gravitational waves simultaneously with the others. This allows us to triangulate where our signal comes from. So the timing of when the signal arrives in each of those three observatories allows us to pinpoint on the sky with some degree of accuracy where the signal comes from, and then we can point electromagnetic telescopes in that area and hopefully find light that comes from the same events. Which is
amazing.
Just a very short question here before we get on to some software you were talking about last time we met. This experiment wouldn't work unless it was in a right angle. If it was just one directional.
Yeah, if it was one direction, it wouldn't. It doesn't have to be a right angle, but certainly if it was just a single direction, it wouldn't work. And the reason for that is reasonably simple. Again, there's just so many noise sources. We're really at the fundamental limit of what you can measure. And so any source of noise looks a certain way. And what we're trying to measure here is actually an interference pattern in the laser beam. And that interference pattern from the light travelling different distances down each of the two arms as they change their length when the gravitational wave passes through. It's that interference pattern that we can measure, but we know what it should look like. And we have theoretical models that we can calculate in supercomputers for what this signal should look like. And so we get lots of things coming out of our detector. Most of them don't look like what we'd expect them to look like. And, again, most of them only appear in one detector at a given time. So you go, okay, we call them glitches. There are different types of glitches. Some of them we understand what they come from. Others we have no idea. There are various lines. There's the 50 hertz line that comes from the power line in the US and things like that. There's all of these different problems that you see. To sort of go back to your question, you really need those two arms going not necessarily perpendicular to one another. You could have them off at 60 degrees. Okay. You'd lose some sensitivity if they weren't. So perpendicular is the optimal orientation for them. Yeah. There's a planned space-based antenna. It's called LISA. It's the Laser Interferometer Space-Based Antenna. And in fact, the plan for that at the moment is to have three arms, each at 60 degrees. And so it's a 60-degree triangle. So you, in some sense, lose some sensitivity because they're not quite at right angles to one another. But because you've got those extra arms in the instrument, that it's three separate spacecraft, each travelling 1 million kilometres from one another. But because you've got the three separate arms, you increase the sensitivity more than what you lose.
And being in space, this eliminates any disturbance or whatever.
Yeah, that's right. So being in space, all of that seismic noise that we were talking about is now nothing to worry about. Yep. You've got other problems. You have to measure the distance between your spacecraft very, very accurately, and you have to hold them in that position using micro thrusters and things like that. But that's a beautiful experiment that hopefully we'll see in the next sort of decade.
Well, thank you for that. You mentioned last time we met a new software called the Bilby. Could you explain to us how that fits into this whole field?
Yeah, so Bilby is a cute marsupial, but it's also a software package that we developed at Monash, and it now is used by the entire LIGO and Virgo collaboration around the world. What it does is it takes the little wiggles that we measure out of the gravitational wave observatory. So the gravitational wave observatory just gives us a wiggle in time. We get one wiggle in time of data from each of the observatories, and we match them all up. And you can say, okay, well, I can see a little wiggle. What does that mean for the astrophysics? How do I know what masses of the two black holes? How do I even know they were two black holes? How do I know what the masses of those two black holes were? Were they neutron stars? Where were they on the sky? Were they spinning, with respect to each other, or, and understanding whether they're spinning can tell us how they formed and things along those lines. Is that signal consistent with what we predict from general relativity? All of these different types of things. This is what Bilby does. Basically, it stands for Bayesian Inference Library, which is a backronym. We actually just wanted the cute marsupial name to be first.
I was going to ask you that.
Yeah.
An endangered species, I believe.
Let's
hope your equipment isn't.
That's right. So we don't have a lot of funding, but we have put a little bit of support into the Melbourne Zoo when we had a conference, so to support the Greater Bilby. So it does that data analysis, which can be very expensive. So it runs on a supercomputer. It often runs on, we've got supercomputers partially funded through our Ausgrav collaboration, which is a sort of what's called a centre of excellence supported by the Australian Research Council that spans a lot of universities. And this supercomputer lives at Swinburne University. And, we run a lot of our Bilby software on that local cluster to tell us, as I said, you get a wiggle out of the instrument. What does it mean astrophysically? And that's what Bilby does. It tells us what it means astrophysically.
So what results has the software actually produced to date?
Yeah, that's a great question. So a lot. And the fact that it's now being used by the entire collaboration means that any new event that we detect, and we're detecting probably a couple every week at the moment because the instruments have just got more and more sensitive over time. Every new event that's measured is run through this Bilby package to try and understand the astrophysics. Now, a lot of those events that we're detecting these days are what we call vanilla black holes. And I never thought I'd say this prior to 2015, but they're just boring. We've seen it all before, whatever. But Bilby's done a lot of really interesting things. So a former PhD student of mine, Isabel Romero-Shaw, was heavily involved in the initial development of Bilby. She's now a postdoc over in Cambridge at her office is 2 doors down from where Stephen Hawking's was and things like that. She's absolutely wonderful. So she had a beautiful paper where we were the first to analyse one of the particular events. It was an event with the very popular name of GW 1905-21. Well, all that is to say it happened on the 21st of May in 2019. We're not very creative with our names. This event was at the time the most massive black hole binary we'd ever seen. Really, really heavy black holes, sort of upward of 70, 80 solar masses, so 70 or 80 times the mass of our sun. And when we analysed that with Bilby, what Isabel was able to show was actually that the orbit of the binary looked different to any other orbit that we had seen. And the reason is that it looked like that the two objects were on an eccentric orbit. So normally black holes are very circularly orbiting one another. These two were on really eccentric orbits. Now, this might sound like a really academic result, but it actually tells us how these black holes formed. And so what we think is, or the current sort of leading theory is that this system formed separately as two separate black holes somewhere out there in a galaxy or in a dense stellar environment, like something called a globular cluster or an active galactic nuclei disk or something along those lines, but in a really sort of dense environment. And they traveled around for a long time by themselves, independently, just zipping in and out of various locations before they actually found each other. And then they found each other and very quickly merged once they sort of reached each other's own gravitational attraction. So this was the first time that we had ever seen a system where we could really almost definitively say this thing comes from a binary that has merged in that way, that sort of found each other dynamically, we call it, rather than two sort of a binary star system that both stars go supernova and then they eventually merge after sort of 100 million years. And so this is really starting to tell us, how these systems form in the first place.
Sounds like a beautiful relationship, Paul.
Yeah, actually, Isabel does, when she gives talks, she does talk about, the relationship between black holes and whether they're sort of, have this de facto relationship, or she does it. I can't do it justice the way she tells her stories, but it's really good, amazing.
Eden.
Last time we met, we talked about the Bilby, and thanks for explaining that to us, but you also mentioned gravitational memory. And this really is fascinating. What is this?
Yeah. And look, I'll put a plug out. If anyone can get access to the August edition of New Scientist this year, there's a really great article in there about, the front page article is actually about gravitational wave memory, written by an amazing journalist, Abby Beale, who I'm interviewed in there along with a bunch of international colleagues. And there's a wonderful article, wonderful explainer. So, what's memory? Memory is a very weird thing. It was predicted in about 1974 by a student at the time, Alexander Polnarov, who I met only a couple of months ago. And so this was 50 years ago that he discovered this effect. We were talking before about a gravitational wave. It passes between you and I, and the physical distance between us oscillates. It goes back and forwards as the gravitational wave passes. It actually turns out, we believe, that after the gravitational wave passes through, our distance has physically changed over what it was prior to the gravitational wave passing through. So, an extreme example is if you and I are initially a metre apart, then after the gravitational wave passes through and everything settles down, we will then be, 1.1 metres apart or something like that, an extra 10 centimetres. Of course, that's not how big the effect is. If that's how big the effect is, it'd be very easy to measure. The effect is incredibly tiny. It's 10 to the minus 22 or something. It's ridiculously small. That's sort of the change in length. So that change in length is 0.000, count up 22 zeros and then a 1, right? So that's small. But we're trying to measure it. We know how to measure it using gravitational waves. It's too small an effect to measure with any given gravitational wave signal that passes through. But what we can do is we can statistically say over all of the measurements that we made, we've made 100 measurements of these binary black hole systems now. Over that period of 100 measurements, we can accumulatively figure out that memory existed in all of those in a statistical sense. And so we can make that measurement eventually. Now, we haven't been able to do it with 100. We think we can do it with around about 1,000 measurements. So we're hoping in the next sort of few years, 3, 4, 5, 6 years, we'll be able to make that measurement. This is something that we're driving out of Monash University. We've had a couple of PhD students working on this now. So Moritz Hübner was a PhD student who's now left and working in industry, and Shun Chung is a new PhD student who's taken up the reins on this search and developing the algorithms and really running the data, and it's quite an intensive sort of search. So this is what we're trying to do. Again, it's sort of the way I've explained it there. It sounds like a really sort of an academic exercise, and why would you try and measure this thing? It's it's great. We can predict that it's there and it should be there. And there's some truth to that, but there's also a really confusing thing that I don't think anyone in the world truly understands, but there's a relationship between this memory, this gravitational wave memory, and things like people who are talking about quantum gravity and how quantum gravity works. And there's this sort of fundamental aspect of quantum gravity that people believe should exist. It's very much in a mathematical way related to memory. People understand how they're related in a mathematical way, but people don't yet fully understand how it's related in a really physical way. So if we go away and measure this, and I was at a conference a month ago asking world experts on the quantum gravity side of this, I'm trying to measure this. If I go and measure this tomorrow, what are you going to learn about the universe? What does it tell us about quantum gravity, about our search to understand a really fundamental theory of gravity? And they said, we don't know something, but we don't know yet. So, we're throwing our hands up a little bit at the moment. People are working on it very hard, and I think there's a really interesting and fascinating avenue here that we don't understand. I think part of being a good scientist is really understanding when you don't understand something. And I think it's true to say in this one, no one understands it, but this is one of those known unknowns. We know what we don't know, and people are striving to do it. So me and my group at Monash, together with Eric Thrain, who's another professor here at Monash, we've been really working hard to try and measure this effect. We're the ones that understand the data at the fundamental level. We understand the black holes, how they merge, and these kinds of things, the type of signal we should be looking for. We've got the software. We know how to do it. But people all around the world are really striving on the other side of things, this saying, okay, if these guys detect it, great. What have we learnt? And I'm hoping that'll be a story that'll unfold in the next few years at the same rate as when we actually make the measurement as well.
Paul, does quantum entanglement take a place in this?
No.
separating electrons and then... No, there's no relationship at all. Okay.
No.
That's fascinating. Finally, there's a big congratulations to your appointment as Executive Committee of the Australian Gravitational Wave Observatory.
Thank you.
I'm not too sure how long ago that was, but congratulate you. Where are we going in Australia when it comes to... We're hearing all sorts of things about maybe we might get a detector here. If you could fill us in on a little bit on the past and where we're going in the future, are we in for a surprise?
Look, we're not in for a surprise anytime soon.
Okay.
This is sort of very early phases. So, to say a little bit about this, we have this thing called the Centre of Excellence for Gravitational Wave Astronomy. It's called AusGrav. That's sort of on the order of $40 million over 7 years for over the next upcoming 7 years. We've got a renewal of funding, so that takes us up to 2030. 8 universities around Australia to do gravitational wave science. In a very broad sense. That affords us the opportunity to do some long-term planning, which you don't always have in science because you're on short-term grant cycles and things like that. In terms of our long-term planning, one of the things that the international community has recognised is that the next generation of gravitational wave instruments really requires instruments spread across the globe. And it really is that triangulation effect of saying, well, how do I work out where something came from on the sky? I really need a long baseline of between my instruments so that I can get timing difference between when signals arrive and I can pinpoint where something comes from on the sky. So there are planned detectors in the US, or a planned detector in the US called Cosmic Explorer, slated for the mid to late 2030s. There's a planned detector in Europe, again, mid to late 2030s. That's something that they're calling the Einstein Telescope. And if you think about where is the optimal place to put a third observatory to get a triangulation, it's something in the southern hemisphere. Yeah. Where's the land in the southern hemisphere? It's here or South Africa. Or, Brazil's probably not optimal given the... you need something that's flat for 40 kilometres, So just in terms of that triangulation, Australia's great. In terms of the seismic noise, Australia's great. Australia's really quiet.
Would Murchison in Western Australia be a possible
Murchison's
spot?
A really interesting spot. Absolutely, it's a possible spot. It's flat. It's incredibly flat. There's infrastructure out there. There's scientific instruments. One of the difficulties, and so to step back, Murchison is where the square kilometre array is being housed. There's the Murchison Wide Field Array, ASCAP. There's a lot of radio instruments out there. It's great for radio because it's radio quiet, which is to say there's not people wandering around with mobile phones and things along those lines. The problem from our perspective, from a gravitational wave perspective, is really just the extra cost. We need people on site more than the radio observatories do. So they've got an initial build cost that for putting it in such a remote location. We'd have that initial build cost that would go up, but at the same time we'd have an ongoing running cost that would cost more because you've got to house people out there. And that's not just a financial cost, that's just a people cost as well. So, where Murchison is an option, but we've done an initial site scoping study within Australia. There's so many places you can put it. Australia is so wonderful. You could... look, I want to put it near a winery. People have shot down that idea.
And a good restaurant.
Exactly. There's so many wonderful places out. Yeah. But in all seriousness, we actually have a location about an hour outside of Perth called Gingin, and we've got a 40-metre high optical power test facility. So basically, we have a very mini laser interferometer there, but it's not designed to do astrophysics, but it's to do tests of infrastructure, tests of equipment, research and development. You can actually extend that site out by around about 8 kilometres, possibly even up to 12 kilometres, which for third generation instruments you might even need more. You might need up to 20. But a site like that exists. It's flat. You can part of the huge cost, if you have to drill through a mountain, it costs you a lot of money. If you have to dig out rock, it costs you a lot of money. Sites like that are flat. That's not the only one. There's loads. There's loads through Victoria, New South Wales, Queensland, Adelaide, South Australia. I can't remember the names of states. There's loads of them. So you've got to figure out. Look, we're miles away from this point, but just to say, Australia is blessed with loads of wonderful land opportunities for something like this. We're in the process at the moment, so we've formulated this committee which is tasked with really just trying to understand the feasibility of such a large-scale investment in Australia and a large-scale project. They really are sort of $1 billion investment.
I was going to ask you that, or any change out of $1 billion?
No, you won't get any change out of $1 billion. And so in terms of, Australian GDP, that's probably bigger than any other science infrastructure that we've had. So it's really, you're talking about international partnerships. And there's lots of opportunities there. And that's one of the things that we're investigating and really trying to understand the international landscape as well as the national landscape, the appetite to do things like this. And there is, and we're in close collaboration with the US, with Europe. China is very interested in a lot of these kinds of things, which socioeconomically is great, but has a lot of other political issues for obvious reasons. But there's wonderful scientists all over the world who are very, very interested in things like this, and people generally all over the world acknowledge that if you're going to build one in the US, you're going to build one in Europe, then you need one in Australia. And so, we're pushing on that. It's a long road, but we're really at the early phases. We need to understand ourselves what would be the optimal instrument that you would want to build. What's the timeline? What's the initial sort of budget estimates, and how do you go about doing that? And so we're doing that. We're understanding what would be the science return on that, as well as the economic return. You're building in Australia. Your cost might be $1 billion, and hopefully there's a lot of international partnership to that. But the amount that does for local industry, local training of people, expertise, the government keeps telling us we want to keep developing, which, absolutely we do. We do a lot of that within big infrastructure builds like this. So this is something we're pushing forward. It's very, very early days, though. And we are really talking about if you want to build something like this, it's mid to late 2030s when you'd be really starting to collect gravitational waves, which means that you've got to get your act into gear now, but we're really not going to break ground until, whatever it is.
This will be the first one in the Southern Hemisphere. Would that be right?
That's right.
Yeah,
that's
so
right.
that's a good argumentation.
Absolutely.
Well, not a whole argumentation, but...
That's right, yeah. And look, we've got a long history of gravitational wave detectors in Australia, in the sense that over in Western Australia, before people worked on these interferometers, people worked on what are called bar detectors. And they built a huge niobium bar over in Western Australia. People like David Blair, who's an emeritus professor over there now, and still very active in the field, and is sort of a larger-than-life character. Is just wonderful. Just written actually book on the history of gravitational wave detection in Australia, and sort of traces it the whole way back to the first observations of eclipses in Walhalla back in 1922 and things like that. It's really wonderful. He was driving forward gravitational wave detection, he and a lot of colleagues driving that forward for many decades. We've been hugely involved in the LIGO projects within Australia. We build and commission a lot of the instruments here that, they get built over here and then shipped over, and our people go over and install and things like that. We do a lot of the data analysis. As I mentioned, that software that we developed is now being used by the entire collaboration. There's a whole host of different things like that. So we're huge players. And I think it's fair to say we probably punch above our weight in terms of the international community. So we're trying to investigate what that next step is, whether we can really go up and beyond and build an instrument in Australia as well.
Time we had one here, Paul?
Look, if you want to start the movement, Eden,
we'll get out there.
Get the political movement going.
Professor Lasky, thank you for joining us to talk to us about the cutting-edge technology of the new field of astronomy on Spaced Out Down Under.
Thanks for having me.
I love the local news.
I love the music variety.
And all the local sport.
24 hours a day, it's all local. 88.6 Plenty Valley FM.